Consider a fairly standard industrial robot with 6 rotational joints. I'm going to add a coordinate frame on link 0 and going to add a coordinate frame on link 6, which is the end effector frame, the bit of the robot that actually does the work. And we've talked about kinematic models which relate the pose of frame 6 with respect to frame 0, and that's a function of the 6 joint angles of the robot. Let's say now that this robot exists in a factory, and the factory's got its own world coordinate frame indicated over here. And we know the pose of the robot's link 0 with respect to the world coordinate frame. We call this the base transform of the robot. The pose of the robot's end effector in the world coordinate frame can be obtained very simply by compounding the base transform with the forward kinematic transform of the robot, which is a function of the robot's joint angles. Imagine now that I introduce another robot, and this one's hanging upside down from the roof, and we know its pose with respect to the world coordinate frame. Then we can write an expression for the end effector pose of this second robot with respect to the world. Now let's look at the tool end of the robot. The kinematics gives us the pose of the robot's end effector, but typically it actually just gives us the pose of some mounting flange on the end of the robot, and we would like to affix some sort of tool to that. So we can introduce a tool here. This is some kind of grinding tool that the robot is carrying. And of course we're interested in the business end of this particular tool. We want to know the pose of this coordinate frame here. With some careful measurement we could determine a relative pose from frame 6 to frame E, and this would be a constant relative pose. So now the pose of the end effector with respect to the world coordinate frame can be written by this set of compounded poses. It's the base transform compounded with the kinematic model of the arm compounded with the constant tool transform from the mounting point to the business end of the tool. Here's one of our previous MATLAB sessions where we're working with a model of the Puma 560 robot. We can see here under the table of the Denevert-Hartenberg parameters that there is a base transform matrix and a tool transform matrix, and each of them correspond to 0 rotation and 0 translation. We can easily change the base transform of the robot, for instance, by adjusting the base property of the serial link robot object. So I might change the translational part of the base transform. Perhaps I will place the robot at 10 meters in the X direction and 15 meters in the Y direction, and maybe I'll put it up a little bit higher. I'll move it up 2 meters in the Z direction. So now the robot object has got a different base transform. So if I now compute the forward kinematics of the robot, these are taken into account, and we can see that the end effector position now is quite different. The base transform is a very powerful function, and I could set a more complex base transform. For instance, I could actually turn the robot upside down. I'm going to rotate it around the x-axis by pi radians. So this is what the robot base transform looks like now, and if I again compute the forward kinematics for that same set of joint angles, we'll see that the position of the robot end effector is different, and we can see that the orientation of the end effector is very different. The positive and minus signs in the rotation submatrix are in different locations. So I've effectively moved the robot and turned it upside down, and that's very, very easy to do with this concept of a base transform. The other thing that I might want to do to the robot is to add a tool transform to it. I do that by adjusting the tool property, and I might declare that the tool has got an offset of 0 in the X direction, 0 in the Y direction, and perhaps it's 0.2 meters in the Z direction, which is pointing out of the mounting plate on the end of the robot. And now you can see that the tool transform represents a finite displacement. And now if I again compute the forward kinematics for that particular set of joint angles, we'll see that the end effector position is slightly different because now it's taking this tool transform into account.